Hello everyone, my name is Vivian Adelowoto. I'm here today to present my capstone project on predicting inpatient hospital length of stay. This project uses predictive analytics to estimate inpatient hospital length of stay across 5 facilities, which I named A to E. The models built for this project are multiple linear regression, random forest, and gradient boosted trees. The best among the three being the GBT with R squared of 0.76 and RMSE of 1.89 days. Project overview. I analyzed 100,000 patient records from 5 hospital facilities using 28 variables. The mean length of stay across all records is 4.00 days, with a standard deviation of 2.36 days. And the CRIPS DM framework guided me from business understanding through deployment. Okay. Business and analytics problem. The core question for this project is if patient length of stay can be predicted at or near admission time. So if the answer is yes, hospitals can pre-schedule beds, plan nursing ratios, and optimize discharge pathways. So my analytics problem here is framed as a supervised regression task using 28 variables, including readmission count, facility ID, comorbidity flags, and lab biomarkers. Data understanding and acquisition. The admission count is the single strongest predictor of length of stay, ranging from 2.72 days for first-time admissions to 8.29 days for patients with 5 or more prior readmissions. I know this alone explains a large portion of the variance and the top feature in all 3 models. Data, diagnostics, and predictive summary. Data quality checks confirmed the data set is clean and complete. The Simpson's rule check validated that the readmission count length of stay relationship holds within each individual facility. It's not just in the aggregate alone. This is a critical quality gate for regression modeling. Methodology. CRIPS-DM provided the iterative structure for this project. I completed all 6 phases. Business understanding set performance thresholds backed by literature. Data preparation was clean. There were no missing values and no computation needed. All 3 models were trained on the same 80-20 split for a fair comparison. Model building and variable selection. 3 variables were dropped in this project, which are encounter ID, had no predictive value. The second one is visit date, not useful as it is. And the third one, the final one, was discharge disposition, which is only known after discharge and will cause data leakage. So the remaining 24 predictors were used across all 3 models for consistent comparison. Model results and performance comparison. Multiple linear regression failed to read the threshold of 0.265, as can be seen here, which confirms that the length of stay predictor relationships are not fully linear. So the random forest and gradient boosted trees both met all targets. GBT is the recommended model here for this here, which has because it has R squared of 0.676, RMSE of 1.89 days. And this means that the random forest and gradient boosted trees met, 2 of them met the threshold. Okay, meaning predictions are off by less than 2 days on average. Next slide. So here we can see that the gradient boosted trees was the best model for this project and is highly recommended for deployment. The feature importance plot confirms what EDA showed. The readmission count is that's the primary driver here. You can see it accounts, just this readmission count alone accounts for 28% of model importance, followed by facility. All variables in the top 10 were clinically plausible, which builds confidence in the model's validity for stakeholders. Analytics solution, how it addresses the problem. This is where the analytics directly answers the business problem. At admission, the GBT model runs in real time and outputs a predicted length of stay. Hospital operations teams use this output to pre-book beds, schedule discharge planners, and notify housekeeping. So the result of this is beds turn over faster and patients wait less. Cost analysis and business justification. The financial case is straightforward. As we can see here, a 0.4D reduction in average length of stay achievable with a well-calibrated predictive model translates to over 18 million plus dollars in avoided costs annually across 5 facilities. Implementation costs are under 120,000 in year 1, giving a return on investment ratio exceeding 100 to 1. Model validation and external calibration. Cross-validation confirmed the model is not overfitted. External calibration against Tujman et al. And Dagestani et al. Showed my GBT results are consistent with the published literature, which gives clinical stakeholders confidence in deploying this model in a real hospital environment. Model plan, deployment plan and model life cycle. Deployment is staged deliberately here. Shadow model. The shadow model in phase 1, means clinicians can predict, can see predictions without being bound by them. And this builds trust before any operational changes are made. And the sharp values in phase 2 gives every prediction a plain language explanation, which is what clinical staff have consistently asked for in similar rollouts. Future challenges and recommendations. The biggest structural limitation in this data set is that it is self-contained. And I cannot assume the model will generalize to a hospital with a different patient population or electronic health record system without testing it first. So that external validation step is most critical. Yeah, is the most critical recommendation for any organization looking to adopt this model. Conclusion. To close, I came in with a concrete business problem, which is hospitals cannot predict length of stay reliably. And I'm leaving with a validated solution. GBT at R squared of 0.76 and RMSE of 1.89 days is production ready, financial justifiable, and grounded in published literature. So the next step is a 60-day pilot at Facility A. Thank you very much, and questions are welcome.